In this video, we are going to go over how to use the knowledge that you have above the atomic structure, so figuring out how many protons, neutrons, electrons are in the atom, knowing what the configuration of that atom is to draw Lewis and Bohr models. So I'm going to do a few of these with you, and then we're going to see how it goes. So you are going to need a periodic table out for this. So the very first one says lanthanum. So lanthanum's symbol is La. If you look it up on your periodic table, this one's hard to find because we don't use it that often. It's element 57, which means its atomic number is 57, and therefore it's going to have 57 protons, and I can put 57 in the bottom left-hand corner of the symbol. Now its mass number. Remember, I have no way of determining the mass, right? I don't know neutrons, so I can't figure the mass out on my own. So I'm going to take the periodic table mass and round it to a whole number. So the mass number here is going to be 139. If I subtract my mass from my proton number, I will get my neutrons, which is 82. I can go here and put my 139 in the top left-hand corner. But in this case, they told me the electrons. So now that I know the electrons, there's two things that I'm going to know. The electron number is going to allow me to figure out the charge. If you remember, P minus E equals C. So 57 minus 55 is going to give me a charge of plus 2. So you want to write that in there. And because I have 55 electrons, instead of, for the configuration, I'm going to go to element 55, which if we look at this, let me see if I can't find it here. So cesium is element 55, this one right here. Now the reason I'm using CS as my configuration and not the configuration for La is specifically because La's configuration assumes the charge is 0. Remember, that's not a charge number in the top right-hand corner. That's an oxidation state. We're not going to use that yet. And this configuration would add up to 57. That's assuming this La has 57 electrons. Our La does not. It has 55 electrons. So I need a configuration that adds up to 55 total. Well, that's element 55. And so 2 plus 8 plus 18 plus 18 plus 8 plus 1 is 55, and that's why I use that configuration. So 2, 8, 18, 18, 8, and 1. So that's the configuration that we use. And then that's that problem done. Now I am going to do a few more with you because if you notice, these jump around. If you've been doing the quizzes that we've been doing, you should be pretty good at this by now. But let's go down to one that throws everyone off, thorium. So thorium the symbol is TH, and this thorium has a charge of plus 1. So when you look at thorium, its atomic number, find on the periodic table, is 90. So it has 90 protons. I put 90 in the bottom left. For this thorium, I do not know the configuration, I do not know the mass, so I'm going to look up the mass on the periodic table. 232 when rounded, so 232 goes there. The charge is plus 1. So two things I can figure out now. One, if I subtract the mass from the atomic number, I will get the number of neutrons, 142. And if I subtract P minus E to get C, 90 minus X equals plus 1, I should get 89 electrons. The reason I want to do this problem is everyone has trouble with this, because what they do is they look for a configuration and then they go to thorium and they say, hey, mister, thorium does not have a configuration down here. So what do? You are correct. Thorium does not have a configuration. That's not your answer. So if we look at thorium's configuration, that's if it were to have, it doesn't have a configuration when it has 90 electrons. Our thorium has 89. So if we go to element 89, there is a configuration present. So then you can use that configuration. And there's just one more trick. So we did mention that the orbitals have a maximum number of electrons, right? So you should know that the way it goes is the first orbital can only fit 2, and your second orbital can fit 8, and then your third can fit 18. So if I look at this, the first number is 18. That doesn't make any sense. There's a reason. See how there's a dash in front right here? I'll highlight it. And then it actually tells you right down here. Denotes the presence of 2, 8. So anytime you get an element, and this only really happens with the larger elements that have more electrons, where it starts with a dash, it actually starts right here with HF. That's the first one, that's the star. Everything after that, they just leave a dash. They don't put a star on it anymore. So since it has that dash, what they're really telling you is the configuration for AC is 2, 8, which isn't written, then 18, 32, 18, 9, and 2. So basically, when you get bigger than 72, if you see the numbers, there's a 2, 8 in front of all of them. And the reason they didn't include it is actually very simple. There wasn't enough room in the box, and if they tried to make the boxes bigger to fit the 2, 8, then it wouldn't have fit on the page, so they would have had to make the writing smaller, and then it would be hard to read, so you get the idea. They said, we're just going to get rid of the 2, 8, because they all start that way, so ignore that part. Everyone here should be smart enough to figure that out, and that's what chemistry does a lot. Now, there is one more part to this worksheet, and a lot of people don't read it, and we're going to mention it now. So on a separate sheet of paper, you are going to draw the Bohr and Lewis models for all of these. So that makes this work a lot more. So I'm going to use the back of my other page. Now, you could use the back page for this if you wanted. I recommend a separate sheet of paper, and the reason being is that I want to be able to look at the information I have on the page and then do my Bohr and Lewis. So my Lewis is really simple. For this symbol, I just go, for the Lewis model, I use the symbol and the charge. I do not write in the atomic number. I do not write in the mass number. That does not go into Lewis. And then I use the number of valence electrons, which is the last number of the configuration, and that's how many dots I get. So it gets 1 dot. Just to go over the dot pattern real quick, first dot goes on the top. Second dot would go on the side. Third would go on the bottom. Fourth would go on the left side. If there was a 5th dot, it doubles up on the top. Dot 6 would double up on the right, dot 7 would double up on the bottom, and dot 8 would double up on the left. You'll never draw anything above 8 dots, so don't worry about going higher than that. Now, for the Bohr model, here's what it's going to look like. We draw a nucleus. We put in the protons and the neutrons, which I have from here. So 57 and 139. Then we draw our orbitals, and we draw as many orbitals as we have electron numbers in the electron configuration. And we label them. The first orbital has 2 electrons. That's this one. Second orbital, 18 electrons. Then another 18. Oh, I made a mistake. So let's fix that real quick. So my second orbital has 8. My third has 18. Then another 18. Then an 8. And then finally a 1, which is your valence electron, which is why that problem only has 1 dot. All right, and so that is your Bohr and Lewis. So you're going to do Bohr and Lewis models for all of these. It may not fit on 1 sheet of paper. It may, depends on how big you write. But if you write big, then just use 2 sheets of paper or whatever you need.